Welcome all of you. This is lecture number 3 for the module 1, and in this lecture we will see that the other representations of the binary number representation in which we can represent the sign of the number as well. So far we have seen that we have represented the unsigned numbers. So today in this lecture we will see how to represent the signed numbers. So various representations like sign magnitude representation, 1's complement representation, 2's complement representations in the binary number system we will see, and we will also perform and see the arithmetics on these signed representations as well, and then figure out that which particular representation is more suitable for the computers, such that we can use that representation and we can perform the arithmetic operations. As well as we will see that how to represent the not only numbers, the characters as well, character data also we can we need to represent to do the computations, or we need to do the programming. So that also we will see in the today's lecture. So far we have seen that in the previous lecture particularly we have seen that we represented the unsigned numbers, but for using unsigned numbers I cannot do the subtraction operation. So for doing the subtraction operation I need to represent the negative numbers as well. So for representing the negative number we need to store the sign of the number, whether this number is positive or negative. So I need to store the sign as well. So now the question is how to store the sign of the number. So can we do same unsigned representation can be extended to store the sign information along the value? So we can say, okay, some portion of the number tells okay to the magnitude or the value of the number, and let's say 1 or 2 bit or something like that can say that okay, this is the sign of the number. So question is how to do it. So let's say the simplest method, or I can say the first the approach which comes to my mind is to, let's say, add one extra bit and that is the left side to that number, and that bit will indicate whether the number is positive or negative. So I can say for positive I can use 0 as that bit, extra bit which I am going to add it, and for negative number it is 1. So let's take an example here. You can see that, let's say, number is, so first 4 bit of the rightmost 4 bit of the number is telling me the value, and the leftmost 1 bit this is telling me about the sign of this number. So here sign is positive, so this is plus 15. Similarly here the rightmost 4 bit is telling me the value of the number. Value of the number is, you can see here it is 15 again, because 1 1 1 1, so 4 ones are 15, and the sign bit here is 1, sign bit is 1, so that's why it is number is, I can say it is negative. So this representation is fine, 1 extra bit is required, and I can represent the positive as well as the negative numbers. So now in this representation, if you look at, let's say in this table, let's see that the 3-bit combination I am using for representing the number. So using 3 bits, what numbers I can represent? So the 3-bit sequence I have wrote here from 00 to 0002 111, and the 00, so first 2 bit is the rightmost 2 bit is the value of the number, and the leftmost bit is the sign bit. So the first is, this is 0, so this is equivalent, second this number is equivalent to 1, and this number is equivalent to 2. 1 1, so this number is equivalent to 3. So 1 1, the decimal value for the 1 1 is 2 raised to the power 1 plus 2 raised to the power 0, so 2 plus 1 it is 3, and the sign is 0, so that's why. So plus I have not mentioned here, okay, let me mention. So 0 anyway, no need to put it, plus 2 and plus 3. What happens here? 0 0 means a value is 0 and sign is 1, so it is minus 0. Here value is 1 and the sign is 1, so it is minus 1. Value is 2 and the sign is minus, so it is minus 2, and this is minus 3. So this is the way how to represent, and this particular representation is called as signed magnitude binary representation. Now here you can see here what is the representation of 0. So you can see here one representation of 0 is corresponding to this row. So you have 0 0 0, and another representation of 0 also you can see here. This is this one. So that is 1 0 0. There are two representation of the 0. One is for a plus 0, one is a minus 0. And for a given number of bits, let us say n bits are given, what is the range of number which I can represent using this sign magnitude representation? So here essentially what we are trying to do, if you compare with the unsigned binary representation by using the 3 bits, how many total numbers I can represent? 2 raised to the power 3, that is 8. So here with the 3 bits, what we are trying to achieve, positive numbers as well as the negative numbers. So half of the combinations will be used to represent the positive numbers, and half of the combination of these 3-bit combinations will be used for the to represent the negative numbers. So like that so total combination still will be 8 only. So how it will be divided, that we have to look at it. So what will be the range? So range will be, if I say 2 raised to the power n minus 1, that will make me half. This is the most negative number, minus 1, 2, maximum it will go again 2 raised to the power n minus 1 minus 1. So let us say n equals to 3. So in case of n equals to 3, what is the range? Put n equals to 3. So range will be 2 raised to the power 2 minus 1, 3 minus 1, that is 2. So 4 minus 1, 3. So it will be minus 3 to, again it is plus 3. Let me write plus here. And in between definitely 0 is there. So essentially plus 1 to plus 3, 3 numbers, minus 1 to minus 3, 3 numbers, 6, and 2 representation for the 0. So that is the range of number I can represent with the help of given n number of bits. Now representation is fine. Now look at the computation part or arithmetic operations. Can we do correctly the arithmetic operations in the case of sign magnitude representation? So how to perform the subtraction, that was the important question. So to subtracting, now we have the way to represent the negative numbers. So let us say I have to subtract from B from A. So A minus B essentially I have to perform. So what I will do, I will represent number B in negative. Whatever the number is given, I will take the negation of that number. I know how to represent the negative number now, and then add to the A. So that will give me essentially A minus B, or the subtraction operation can be performed on that. So now let us try one example here. So here 2 numbers are represented. Now these 2 numbers are represented in a sign magnitude representation. Don't confuse with the unsigned representations. Now whatever number we are taking in a signed representations. So which particular sign representations we are using currently, that is sign magnitude. So here this number A, you can see the number is the negative, because here 1 is there. So number is negative. So what is the value? Minus 5. 101 is 5. Because number is negative, it's a 5. Second number is what? Number is positive because leftmost bit is 0. So it is plus 5. So what is the expected answer? 0. Plus 5 and minus 5 addition should give me 0. So let's do the addition as we did in the normal binary unsigned binary representation. Same addition I am trying to do it with the signed representation. So 1 plus 1, same binary addition table will work here, same rules will work. So 1 plus 1 0, carry equals 1, 1 here, 1 plus 1 0. So here carry is 0, so 1 plus 1 0, carry is 1, 1 plus 1 0, and final carry generated from the last block or leftmost block is 1. So this is the result I got. So the 4-bit representation is there. So in 4-bit what result I got? So how to interpret this result in sign magnitude form? Leftmost bit is 0, so number is positive. What is the value of the number? 0 1 0 2, so it is 2 plus 2. What was the expected answer? Expected answer was 0. What I got? 2. Means the simple addition method will not work when I am dealing with the sign magnitude numbers or numbers in binary with the sign magnitude representation. We need to do something to get the correct result, means my circuitry will be complex. Or in simple words I can say that this addition is not straightforward, or the operations, arithmetic operations on sign magnitude representation is not straightforward. So right now we are not looking in terms of okay what additional things has to be done to get the correct result, but we look at other representations first. What are the other ways? Maybe in one of the representations we will get the correct, the simple method of addition works. So let's look at the another representation. So to represent in one more method, let's try. Let's say negative numbers we represent by flipping the bits. Flipping bits means one bit, the digit 1 will be flipped to 0 and the digit 0 will be flipped to 1 when I will try to get the negative of that number. So positive number represented as it is as an unsigned numbers, and negative numbers will be just flipping the bits of the corresponding positive number. Look at example. So let's say 3-bit representation of plus 2 is what? 0 1 0. 2 I can represent with the help of 3 bits. In the case of sign magnitude representation already seen in the table. So what will be the representation of minus 2? Take the 1's complement. So that is called as a flipping the bit is called as a 1's complement. So what is 1's complement? Just flip the bits. So this 0 becomes 1, this 1 becomes 0, and this 0 becomes 1. So what I am getting here? 1 0 1. So this is minus 2 in 1's complement form. How to represent minus 2 in the sign magnitude form? Simply putting in place of 0 1 here. In case of 1's complement, just flip the bits of the corresponding positive number. So this is minus 2. Now the way in which we look at the sign magnitude 3-bit table, number representation table, we will look at the in the 1's complement representation as well. So here the same 3-bit combinations I have used, and the corresponding numbers in the 1's complement which are shown in the decimal format or decimal number system are like that. So here my 0 is this, 1 2 positive numbers are as it is, there is no difference between the unsigned numbers and even the sign magnitude also. So positive numbers are represented as it is. Negative numbers you can see here. So what is the minus 1? How will represent the minus 1? So to represent the minus 1, I have to take the 1's complement, or I have to flip all the bits of this 1 representation of 1. So it will be what? 1 1 and 0. So 1 1 and 0 will be 1 1 and 0, that is the minus 1. Similarly, what will be the minus 2? 1 0 1. So 1 0 1 means this, so this is minus 2. So like that you can find out the other combinations. Here also you can see the representation of 0. There are two representation of 0, one is here and one is here. One you can say this is plus 0, other you can name it as a minus 0. So there are the two representations of 1 are there, and that is the one of the cause of the, you can say, problem. We will see later how it creates a problem. So if I want to find out what is the range of number which I can represent with the given number of n bits in the ones complement form, so again the range will be same. In the negative I can represent with the n bits 2 raised to the power n minus 1, that is the most the negative number, then to 0, 2. In the positive side 2 raised to the power n minus 1 minus 1. Here also what we are trying to achieving in any signed representation, half of the combinations of the total number of combinations with the given number of bits we are using for the positive number representations, roughly half I say, because here is a 2 representation of 0 and half of the combination for the negative numbers. Now representation we have seen, now look at the whether the arithmetic works or not. So quickly look at this ones complement addition of the two numbers, and as I said subtraction also can be done. Now we have the representation of positive and negative as well, so if I have to perform a minus b, then I can take the negative of b and then I can perform, even through the addition also I can perform the subtraction. So let us add these two numbers. I added 1 plus, so first look at what numbers are represented in the ones complement form. So you can see here this is the ones complement form, number is given. So the leftmost bit is here it is 1. So the number is what? Number is negative. So negative numbers are represented in ones complement with how? This is in ones complement form. So I have to take the ones complement of this number. So I will take ones complement of this number. So that will give me just flipping the bit. So flipping the bits means 0, 1, 0, 0. So this is 2. So value is 2 and this 2 is represented because it is negative number, so that's why it is minus 2. This is positive number, so this is plus 5. I will take as it is unsigned binary, so unsigned binary value of this number is 5. This is the negative number, so it is 1, this is minus 2. Let us add it. So 1 plus 1, 0, 1 plus 0, 1, carry 0, 1 plus 1, sum 0, carry 1, 1 plus 1, sum 0, and final carry is 1. So you can see what is the result here. Result is plus 2, and what is the expected result? Expected result is plus 3. So here also you can see that this straightforward addition is not working. So how to, so means for here you can say how to get the correct result. If this final carry, if I can add it here, let's say this final carry I am adding, this is carry which is generated by the last column of the number. If I add it, then I am getting the correct result. So here you can easily understand that, okay, how to, so there is additional one addition I need to perform, final carry. If it's generated, that has to be added to get the correct result. So straightforward addition is not working here. So this representation is also not good for representing the negative numbers in the computers, because this additional, after adding the bit by bit, again I need to, one more addition operation has to be performed, the carry is generated, then I am getting the correct result. So we need to look at let us say we will try one more combination or one more representation to represent the negative numbers. So, as I said that 1's complement representation also arithmetic is not working perfectly, need some additional stuff to do the arithmetic operations, or the straightforward arithmetic straightforward addition is not working. So, we look at one more representation. So, in this representation, let us say to positive numbers again we will represent with the unsigned representation only. For the negative numbers, we need to find a method. So, how to do? So, let us say one method is to take the 1's complement of the number of the corresponding positive number, 1's complement of the corresponding positive number. How to take it? To convert the 1's to 0 and 0 to 1 of that number, and then add 1 to get the negative of that corresponding number, negative of that number. So, let us look at an example. Here you can see the +3 representation in the unsigned binary number representation, that is the +3. To represent -3, I have to take first the 1's complement of this +3. So, taking 1's complement means flipping the bits. So, 1 becomes 0, 1 becomes 0, 0 becomes 1. This is a 1's complement, and then add 1. So, adding 1 means 1 0 0, and then in 1 0 0 I am adding 1. So, this will give me 1 0 1. Now, this is the 2's complement representation. In the 2's complement representation, this is -3. This is equivalent to -3. And this 2's complement representation is applicable to the decimal number system also, in the way that in decimal number system we can call the 10's complement, the 1's complement is equivalent to the 9's complement. So, in all number systems, whether number system is a, let us say it is an octal number system. So, in octal number system also, the 7's complement is equivalent to the 1's complement in the binary number system, and the 8's complement is equivalent to the 2's complement in the binary number system. So, they are applicable to any number system, whether it is octal number system or whether it is a decimal number system or the binary number system. Okay. So, let us look at the 3-bit with the help of the 3-bit, what is the range of number which we can represent with the help of the 2's complement. So, these 3-bit combinations you can see here, and the corresponding 2's complement number is, so positive number as I said as it is will represent, and to the corresponding negative number. So, what is the negative number of 1? So, negative number of 1 will be 2's complement of 1. So, 2's complement of 1 will be 1 1 1. How? Let us look at it. So, 0 0 1 is your 1 plus 1. To make it or to get the -1, what you have to do? You have to take 1's complement. So, I am writing 1's complement here, that is 0, flipping the bits, I flipped it, and then add 1. So, I am saying +1, so that will give you the 2's complement. So, adding 1 will be 1 1 1. So, that is why 1 1 1 is a -1. So, this is the, so similar way the 2's complement of the +2, you will get 1 1 0, that is that will represent the -2, and the 2's complement of 0 1 1, that will give you the +3 representation will give you the -3. Here one interesting thing you can observe, that is there is only one representation for 0. So, representation of 0 is only 1 0, that is 0 0 0 only. There is no notion of +0 and -0, which we have observed in the 1's complement as well as the sign magnitude representation. So, if you look at the range of the number which I can represent with the given n number of bits in the 2's complement is, slightly that formula will change due to this one representation of the 0. So, that representation will be formula will be, in negative we are getting one extra number, So in negative I will say 2 raised to the power n minus 1. That's the most negative number I will get it by using n bits. And then in positive I will get 2 raised to the power n minus 1 and minus 1. So if I have a 4 bits, so using the 4 bit I can represent minus 8 to plus 7. So minus 8 to plus 7, how many combinations? So minus 8, total 8 numbers I represent in negative, plus 7, 7 positive numbers I represented. So 8 plus 7, 15, and one combination is used for the 0, that is 0 0 0. So in case of 4 bits, this will be 4 zeros will be there. So it is total 16 combinations are how. So half are used for positive, half are used for negative, and one exactly half will not be there in case of the negative. So that one representation in the case of positive, so one representation will be used for the 0. Now after representation, let's try the arithmetic, whether the arithmetic operations works or not. We have not succeed in the sign magnitude and ones complement with the help of the straightforward addition method. We have not succeed. So let's see that can we succeed in this case. So let's do the addition operation on 2's complement numbers. 2's complement numbers you can see here. So first number, this is negative number. So to get the number value of this number, I have to take the 2's complement of this number. So first I will take the 1's complement of this number. Taking 1's complement means I will flip the bits and add the 1. So flipping bits and adding will give me 3. So the number is negative, so it is minus 3. So this is the way how to get the value of the negative numbers in 2's complement. Second number is a positive number, so directly I can take this is plus 5. Now do the bit by bit addition operation. 1 plus 1 is 0, sum carry equals to 1. Then here carry equals to 0. So 1 plus 1, sum 0, carry 1, 1 plus 1, 0, and the final carry is 1. So this result is positive and that is equivalent to plus 2. So this is, and here I am getting the correct result which we have not got in the sign magnitude representation and one's complement representation. Straightforward addition was not working. Let's take one more example to verify this result. So let's take two 5-bit numbers. One 5-bit number I am taking 00101 and I am taking both the positive number this time, and another 5-bit number I am taking, that is 00100, and do the addition operation. So 1 plus 0 1 and carry is 0, 0 plus 0 is 0, 1 and carry is 0, 1 plus 1 sum is 0 and carry is 1, and 1 plus 0 is 1 and this final 0 is there. So what is the result we are getting here? The result is, this is the representation of 9. So I am getting here 9. What is the value of the first number? The value of the first number is here 5. What is the value of the second number? 4. Both are positive numbers, so plus 5 plus 4, and the result is also plus 9. So means we have tested two examples and we have seen that the straightforward bit by bit addition is working in 2's complement representation, which was not working in the 1's complement and the sign magnitude form. So this representation looks good in terms of performing the arithmetic operations in the computer. So we will use this representation for the number to represent the numbers in the computers. Now by the same numbers you can represent in the 6-bit form. Right now we have represented in the 4 bits, and we have seen if I add it, I think let me write the result here again. So we got this result plus 2. So if you represent this same numbers 6 bits, so how to represent a number? We need to represent any number, we need some minimum number of bits. that from the formula we can get it. Now, can we represent a number with a given number of bits, and that given number of bits are more than what are the minimum number of bits which you require? Definitely less than minimum we can't represent. So let us say this first number is minus 3 in 2's complement, and the second number is plus 5. So minus 3, I need minimum 3 bits. How to represent in 6 bit? So unsigned numbers, how we represent unsigned numbers? Using more bits. We appended the 0 as a leftmost bit, the required number of zeros at the leftmost bit, and 0 doesn't add anything in the magnitude of that number, so number value is not changed. So same thing we want here. Here also number value should not be changed if I am representing a number with a larger number of bits. So here if I add it 0, let us say I append the 0 on the as a to represent this minus 3 into 6 bits. So 1 1 0 1 is there. If I say 2 zeros, I will add it. Will it change the value? Yes, it will change the value, because now number becomes from positive to negative. So this will not work. So what I have to do? I have to, if I add it to ones, and then the original 4 bits I am writing here of the first number. So 1 1 1 1 0 1. Now what is the value of this number? You can calculate the value. So for calculating the value, because number is negative, so I have to take the 2's complement of this number to get the value. So the 2's complement will be taking the 1's complement and then adding 1. So 1's complement will be 4 zeros 1 and 0 and plus 1. After adding 1, I will get the 2's complement. So I am getting this. So 3 I am getting, and because number is negative, so it's a minus 3. Still the value has not been changed when I represent from 4 bit to 6 bit this number. So it works. So let's say now try the second number. So second number I am trying here. The second number is 0 1 0 1. So if I add to represent this number using 6 bits, if I add 2 extra bits at the left side of this number, 2 once I add it, will it work? Will it the value of the number will remain same? No, because original number is positive. Now I am getting, because this leftmost bit is 1, in 2's complement form it is negative, so this also will not work. So if I add it 0 0 0 0 1 0, that is fine, because as we did in unsigned numbers, we append the zeros to the left side of the number to make it in a required number of bit representation. So what is the conclusion? So conclusion is, if you extend the sign bit of the number, then the value of the number will not change. And so this particular thing is called as a sign extension. So if I have to represent a number with some x number of bits, then I have to extend the sign bit, not 0, not 1. So it will be sign bit I have to extend. So if the number is positive, then I will append 0, in nutshell we can say. If the number is negative, then I have to append whatever the extra number of bits I require to get the desired bit representation. I have to replicate that sign bit. So in case of negative, I will replicate once. In case of positive, I will replicate 0. So same thing if you have to represent in 8 bits. So minus 3 you have to represent in 8 bits. So you will add extra 4 ones. So you replicate the sign bit, and then so minimum number of bits required to represent minus 3 is 3 only. Rest of the bits are replication only. So usually, as I said, the computers have, let's say, 8 bit representation or 16 bit they represent the numbers. So the additional bits can be appended or replicated, the sign bits can be replicated to represent the 2's complement numbers. Now let us look at this particular example. So in this example you can see here two numbers are represented using the 6 bits and these two numbers are in 2's complement form. The value, decimal value of the first number is 26 plus 26 and the second number is plus 10. So now let's add these two numbers. We already seen two addition example and we have seen that okay, the result is coming correct. So let's try this and see what is your observation here. So 0 plus 0, 0 here, 1 plus 1, so carry is 0, so 1 plus 1 sum equals to 0, carry equals to 1, sum equals to 1 and carry equals to 0, 1 plus 1, sum equals to 0, carry equals to 1, 1 plus 1, sum equals to 0, carry equals to 1, sum equals to 1 here and the carry generated from this is 0. Look at the result. Is this result is correct? This result is not correct. Why it is not correct? The first observation or my first observation is that both the numbers are positive numbers, plus 26 and plus 10. Result also should be positive number. Here you can see the result is negative because this leftmost bit is 1. So no need to find out the value of this number. Definitely it is a incorrect result. Why it is incorrect result? So first look at that what are the numbers which I was trying to add in 2's complement form. So number is 26 and 10, so the decimal equivalent will be 36. 26 I can represent with the help of 6 bits, 10 also I can represent with the help of 6 bits. For to representing 10 I need 4 bits and to represent the 26 also easily I can represent with the help of 6 bits. 36 how many bits I require? How many bits I require to represent 36 in 2's complement form? Using 6 bit my number will be in the range of, or I can put this question in other way, what is the range of number which I can represent with the help of using 6 bits in the 2's complement form? So 6 bit the range will be minus 32 to plus 31. This is the range of number which I can represent with the help of 6 bits in 2's complement form. Right? Means 36 plus 36 cannot be represented with the help of 6 bits. This is what is called, it is called as overflow. Means the result cannot be accommodated in the given number of bits. So that's why this result is wrong. We have already seen in unsigned representation when we did the arithmetic operation in the unsigned representation. So now the question is how to detect this overflow in the case of the 2's complement form. So my first simple observation I can detect is, or I can make my system such that okay it can detect. So I need to specify okay this is the condition in which if you are getting this condition is true means the result is incorrect or the overflow has been occurred. So here you can say two positive number I am adding. So the number which I am going to add the sign bit is 0 and the result which I am getting sign bit is 1. So my first observation is you look at the sign of the both the numbers, positive and result is negative. So you can check it if the sign of the result is opposite to the sign of the both the numbers, then you can easily say it's a overflow. Because positive number result also should be positive, result cannot be negative. So outrightly it can be rejected. Second observation is that you look at the what is the carry in the last column. The carry in the last column is 1 and carry out from the last column is 0. If both the carries are different, then also it indicates it's a overflow. Different means either 1-0 combination into out or 0-1 combination. 0-0-1-1 will be no problem. So you can observe or you can do it the last slide exercise again in which we got the correct result where we got the correct result, you observe the what is the carry into the last column of your number and what is the carry out. Is both the carries in these two examples which we discussed are same. Here it is different, so that's why it indicates the overflow. So if you are getting the correct result, there is no overflow, means both these two carries should be same, either 0 0 or either 1 1. Here we are getting different, so that's why it's a overflow condition. So this is the way you can detect the overflow, by checking the sign bit or by comparing the carry in and carry out to the last column or leftmost column of your two numbers. Now look at the, so we have seen that representation, number representation, which number representation is suitable to represent the in the computers. Not only representation, we have also seen the arithmetic operations, doing arithmetic operations on that, and we found that 2's complement is appropriate in terms of arithmetic operations also. Straightforward, we can do it. Simple, the adder circuit, simple addition of bit by bit addition will work for all the arithmetic operations. Addition and subtraction we have seen. Similarly, the division and multiplication also can be represented by using the these addition and subtractions only. So now, what is the data type in the programming language we refer? Data, we represent the data in the to write. If you write a program, let's say you want to add two numbers, or you want to do some operation, arithmetic operation on two numbers, you have to represent that number. So representing that in, that is, you are representing any number in a particular data type. So essentially data type is a set of values which is associated with a common representation and the operations. So if you say my data type is integer, is a data type, let's say in the C programming, that in this course we are doing C programming. So integer is a one type of data type in C, in which integer means what are the set of values I can represent, and what is my representation, and what are the possible operations I can do it. So for any data type, these things are fixed, or I can say these things are specified. What operations you can do, how you will represent the data, and what is the range of value for a given number of bits you can represent. So in this case, here you can see for a 32-bit machine, 32-bit machine means where integer values are represented by using the 32 bits. Any integer number will go 32 bits. So what is the range of number using 32 bits? Minus in the 2's complement form, minus 2 raised to power 31 to 0 to 2 raised to power 31 minus 1. So positive number will be this, the maximum positive number I will get, this is the maximum negative number I will get. Beyond that, the overflow will be generated. Any number which I am trying to represent which is beyond this boundary, either in the negative side or positive side, I will get the overflow. Representation is, I said, in 2's complement, and the possible operations, addition, subtraction, multiplication, division, and this is a modulus operation. Modulus, that gives us the remainder. Now, so here what about the unsigned int? So unsigned int representation, so by using the same 32 bits, the unsigned representation will be, what is the range of values I can represent? No negative numbers, so I will say 0 to 2 raised to the power 32 minus 1. All the combinations will be used for the positive numbers, no negative numbers. So in unsigned number, more positive numbers can be represented with the given same amount of same number of bits, which is used to represent the signed number, signed and unsigned both. So one data type which is integer data type, one is the, you can say, the variation of integer data type, that is unsigned integer. So unsigned integer range will be different because only positive numbers has to be represented. So far we talked about the numbers representation. Representations we have seen, arithmetic operations we have seen, and the one of the data type in C which is available, that is integer data type, that works on the numbers. But what about the characters? Characters also we need to represent. We need to represent the strings, name strings, that also we need to store it, and we need to require to do the operations on the strings as well, on the characters as well. So for that we need some representation for the characters as well. So characters also can be represented by the natural numbers. We can specify, let's say A, B, C, D, E, we can give some number. A means this number, B means this number, C means this number, and so on. How the characters are represented in the C language? So characters are represented in C language using the unsigned integers, because characters don't sign is not required. So the negative combinations, the combinations which are used to represent the negative values in the for the numbers, to represent the numbers, they can be used here. All can be used to represent the characters. So the unsigned integers is more appropriate. So for using 8 bits, the range of the number which I can represent, that is 0 to 255, 2 raised to the power 8 minus 1 starting from 0. That is the range in which I can represent, and use ASCII code to represent the characters. ASCII code is a 8-bit character. So each character is a combination of 8 bits, and 8 bits, what are the total number of representations which I can get? That is a 0 to total number of combinations will be 256, including 0 it will become 256. So what are the characters we need to represent? The English alphabets, uppercase letters, lowercase letter, capital A to capital Z, and lower case a to z. Numerals 0 to 9, punctuations, comma, semicolon, etc., which you can see on your keyboard of your computer. Special characters like question mark, backslash, right, forward slash, asterisk sign, and all these. So all these characters are mapped to a set of unsigned integer values in the range of 0 to 255 to represent the characters. So this is all about the third lecture of this module 1. Thank you very much.